Hi again, everyone. This is the third lecture for Chapter 2. Today we're going to be moving into biochemistry. Specifically, this lecture is going to be looking mostly at inorganic biochemistry. We have one more lecture after this left in Chapter 2, and after the next lecture, that will be the end of Unit 1, and that will be everything that is on our first lecture exam. So let's go ahead and start with our not really attendance questions. First, if a negative sign means something gained an electron, what does a positive sign mean? It gained a proton, it lost an electron, it gained at least one neutron, or more than one of the above is possible. And second, where is a hydrogen bond in a group of water molecules? So I'm going to go ahead and let you guys try to figure those out, and meanwhile I'm going to draw a couple of water molecules so that we can use it to answer that question. So while I'm drawing, try to go ahead and answer those questions. Okay, so let's see what we got on those. If a negative sign means something gained an electron, what does a positive sign mean? So if we saw something like K plus or Ca2 plus, something like that, what does the positive sign mean? Does it mean that it gained a proton, that it lost an electron, that it gained at least one neutron, or more than one? Well, if we see a positive sign, remember if we saw a negative sign, that meant that it gained an electron. Negative signs mean that it gained an electron and now it has an extra negative charge. So positive signs mean that it lost an electron. It seems like a positive should mean that it has an extra proton because it's got an extra positive. Well, it does have an extra positive. That's what the positive sign is telling us. But nothing ever gains or loses a proton. Because if you have an extra proton, if you gain a proton or if you lose a proton, it changes the identity of the element. Remember, the number of protons defines which element we're looking at, and that never changes. Every potassium everywhere in existence will have the same number of protons. Every calcium anywhere in existence will have the same number of protons. So what does the positive sign mean? It means that it lost an electron. In the case of K+, it lost one electron. In the case of Ca2+, it lost two electrons. So the plus sign, it still means that it has more positives than negatives. But the way that it got there wasn't by gaining protons, it got there by losing electrons. Next, where is a hydrogen bond in a group of water molecules? Well, when we have a group of water molecules, the big, what we said was kind of like Mickey Mouse face, that is an oxygen. And then the two ears, each one is a hydrogen. And the oxygen side is slightly negative, the hydrogen side is slightly positive, and that's just because of unequal sharing of electrons. So the hydrogen bond is not the bond between the hydrogen and the oxygen. That is a polar covalent bond. The hydrogen bond is actually that temporary weak bond that forms between the hydrogen of one water molecule and the oxygen of a nearby water molecule. And it doesn't have to be water. It could be anything that has a polar covalent bond. It's between the positive region and the negative region of different molecules or different regions of a large molecule. All right, so let's go ahead and get started with the new material. And we're actually going to wrap up something that we started talking about last time, and this will just kind of pull everything that we've talked about together, and now we're going to talk about energy flow and rates of reaction. So how fast does a reaction occur, and what happens to energy within that reaction? Remember, energy cannot be created or destroyed. It can be converted, or it can move from one place to another, such as if it's lost as heat or something like that. And that's what these first two terms mean, endergonic and exergonic. Sometimes you will also see them as endothermic or exothermic. I'll go ahead and put the EX in there and the END. So endothermic or endergonic, exothermic or exergonic. Those are telling us whether energy is going into the reaction or being given off from the reaction. Does the energy have to be put into the reaction for that reaction to occur? Or during the reaction, is energy being released? So endothermic or endergonic, that is a reaction that you actually have to put energy into it for that reaction to occur. Ender, into. Gonic is energy, or thermic is heat, because typically it's energy in the form of heat. And endergonic reactions oftentimes will feel cold as they are happening because they are absorbing heat from the environment. Heat is going into them. Well, for heat to go into them, they must be cooler than the surrounding environment. So endothermic reactions or endergonic reactions, they require an input of energy for the reaction to happen. Exergonic or exothermic reactions, these are reactions that give off energy. They do not require an input of energy. Instead, as the reaction happens, energy is given off in the form of heat. Oftentimes you will see something like an explosion or a loud pop, or it will give off bright light. All of those are forms of energy that are being given off by a reaction. Now, whether or not energy is going in or coming out, there are different things that will affect how fast a reaction happens, the rate of the reaction. And some things that will affect the rate of the reaction. First, temperature. As a general rule, as temperature is increased, a reaction will happen faster. Next, concentration of reactants. Well, the reactants, remember, they are what are going to go through the reaction. So if there are more of those reactants, then the reaction can happen faster because it's got a bigger pool to draw from. Particle size. Smaller particle size will increase the rate of the reaction. And that's because smaller particles will have a greater surface area to volume ratio. So for having that larger surface area, there is more room for the reaction to take place, basically. Also, the smaller the particle size, the faster it can move, and the more likely it is to bump into something so that it can react. Catalysts. Well, catalysts, by definition, are things that cause a reaction to happen faster than it would otherwise. So that automatically tells us catalysts will speed up a reaction. But the thing about catalysts is not only do they cause a reaction to happen faster, they themselves do not get changed by the reaction. So it's kind of like something that comes along, causes some other things to react with each other, and then it leaves in the same state that it was to begin with. Now, in our body, we have catalysts. And in our body, they are made of protein. So we give them a special name. We call them enzymes. Enzymes are biological catalysts made of protein. Enzymes are biological catalysts made of protein. And there are a lot of reactions in our body that happen so slowly that they would not be able to happen in the course of our lifetime. But enzymes allow them to happen often several thousands of times per second. So enzymes, catalysts, can really, really increase the rate of the reaction. But every time they do that, they themselves are not changed by the reaction that they are catalyzing. We will talk about those again when we get to proteins in chapter 3. Reversible reactions. This may have been earlier in your outline, but I thought that it fit better here because it's going to tie into energy a little bit. We said that when we look at a reaction, whatever the arrow is pointing away from is those things on the other side of the arrow are called the reactants. And then whatever the arrow is pointing towards are called the products. So here we have particle A plus particle B leads to molecule AB. But here we see a weird arrow. It's an arrow with a head on each end. And this just shows us that the reaction is reversible. Going this way, A plus B leads to AB. What kind of reaction is that? Do you remember? That's a synthesis reaction or an anabolic reaction. But going this way, if we start with AB and we break it apart into A plus B, what kind of reaction is that? That's a catabolic reaction or a decomposition reaction. We're breaking something down into smaller parts. Some reactions can only go one way. Some reactions can go one way or the other. We say that that reaction is reversible. Most of the time a reaction is reversible, but not always. Some reactions are not reversible. And typically, reactions that are reversible are endergonic in one direction and exergonic in the other. We're going to see that when we start talking about ATP in the next lecture. We have to put energy in for the reaction to occur, but then when the reaction goes the other way, that energy that we put in is released. So now let's talk about biochemistry, and the rest of chapter 2 we're going to be talking about biochemistry. And there are entire college courses on biochemistry, so we are just whittling it down to the bare bones. This is the chemistry that occurs in living organisms. And biochemistry is categorized with two different branches. There is inorganic biochemistry, which we're going to talk about today, and organic biochemistry, which is the topic of the next lecture. Inorganic biochemistry typically does not contain carbon. Every now and then it does, but typically it does not contain carbon. And inorganic biochemistry deals with salts. Now, salt does not just mean table salt. A salt is a type of molecule between a metal and a nonmetal. So salts, many acids and bases, which we'll talk about later today. Those are inorganic biochemistry. Organic biochemistry, all of these molecules contain carbon. Carbon is the central element for organic chemistry. And usually the molecules are very, very big, lots of covalent bonds. And there are 4 classes of organic compounds. There are carbohydrates, lipids, which are fats and oils, proteins, and nucleic acids. And we will talk about all 4 of those in the next lecture. So as we begin to talk about inorganic biochemistry, the first topic has to be water. Water is the most important substance in our body. Not only is the most important, it's the most abundant inorganic material in our body. It makes up 50 to 75% of our body volume. It makes up 50 to 75% of our body mass. As you are younger, that number is a little bit higher. It's closer to 75 when you're born. And as we get older, that number gets lower and lower and lower, closer towards 50. But it makes up the majority of our body. And water is extremely important for life And there are 4 properties of water that make it so important. And that's what we see here. It has a high heat capacity. It has a high heat of vaporization. It is a polar solvent. And it has cushioning properties. So let's see what each of those mean. If something has a high heat capacity, which water does, it means when you put energy, such as heat, into it, it will hold on to that energy or heat for a really long time. Now, I always like teaching this class in the fall because I can give a perfect example that most students can relate to. After the summer has ended and we start getting some of those cool days at the start of autumn, if you like to go to the lake or the river or something like that, maybe it's a cool day out, but it's still, near the end of summer. You can jump in that big body of water and what do you notice? That water is still really warm. Even though the day may be cool, the water itself is really warm. And that's because the summer has put a lot of energy in the form of heat into that water. And the water will hold on to that heat for a really long time before it cools off. That's because it has a high heat capacity. So why is that important for life? Why is that important in our body? Well, it makes it really easy for us to maintain body temperature. It doesn't take a lot of ATP. It doesn't take a lot of our body energy to maintain body temperature. Because once we have warmed our body up and achieved body temperature, it will hold on to that heat really, really easily. It takes a lot for that energy to be lost from our body because of the water content. Next, heat of vaporization. The heat of vaporization is how much energy or how much heat is required to convert something from liquid to gas. If we're talking about water, it has a high heat of vaporization, meaning that it takes a lot of energy for it to convert from liquid water to water vapor. Let's apply that to the body. When you are warm, when you start to get too hot, what do? You sweat. We start to put liquid on the surface of our body in the form of sweat, and that sweat is mostly water. Now, as that sweat evaporates, we actually have to put energy into the sweat for it to evaporate. Where does that energy come from? It comes from the heat of our body. Blood vessels just under our skin are passing by, and as that sweat evaporates, it's pulling heat out of our blood, cooling it down. And then the blood circulates through our body, in turn cooling the rest of our body down. Next, polar solvent. Polar solvent just means that water is really, really good at breaking things down because, remember, let's draw our water molecule again. Water molecules are polar. If I can get my eraser to work. Water molecules are polar. One end of it has a different property than the other end. One end of it is slightly negative, the other end is slightly positive. Why is that important? Well, let's look at what happens if we put sodium chloride. Remember when we made our sodium chloride last lecture? The sodium side of sodium chloride was what? It was positive. The chloride side was negative. What happens when you put a spoonful of salt into a large glass of water? The salt is going to dissolve. Let's look at why it dissolves and how it dissolves. Well, if we have our water molecules, which we see over here on the right, the positive end is going to pull on that chlorine. The negative end is going to pull on that sodium. And it rips this bond apart so that the chloride goes towards the negative or the positive side of water, and the sodium goes towards the negative side of water. it ripped that bond apart. It was a solvent. Water is really good at doing that. Anytime something goes into our body that has any polar regions at all, water is really efficient at breaking it down. And that's because it is a polar solvent. Water is cushioning. Water is cushioning. Water acts like a pillow. A great example of this is our brain. Our brain is surrounded by a liquid called cerebrospinal fluid, and the inside of it is filled with liquid called cerebrospinal fluid. And the brain itself is pretty heavy. It's a few pounds, and it's really, really soft, so it could collapse under its own weight. But because of that liquid inside that's mostly water, it provides some outward pressure to keep the brain from collapsing in on itself. And since the brain is surrounded by that fluid, if we ever move our head too quickly, it acts as an airbag almost, but made of water. And it keeps our brain from impacting our skull. It acts as a cushion. Most of our body is water, and water is, in fact, a cushion that lets us do things like fall down without just shattering. Now, what I have over here in this image, even though we don't talk about it here, since water has all of those hydrogen bonds, it allows it to form something called surface tension. And that's what we see right here. This little bug is called a water strider. You've probably seen these before. They can walk across the surface of the water. And we can see here in this image, the water surface is just kind of bending rather than breaking and letting them sink. And that's because the water has surface tension, and the surface tension comes from hydrogen bonds, every water molecule holding on to every other water molecule with those hydrogen bonds. Water in the body and reactivity. Every reaction in the body occurs in the presence of water. And water oftentimes can become a part of those reactions. And here across the top, we see something called dehydration synthesis. This is when we take two smaller molecules, remove an H and an OH. The H and the OH make H2O, water. The water leaves, and the resulting two molecules there stick together to form a bigger molecule, synthesis. The opposite of that, if I have a larger molecule, I could put water into that molecule and it breaks it apart. So I'm going to play a video. I don't believe it will play the sound of this video. If it does, great. If it doesn't, I've actually got this inserted into the video in the Blackboard. So go ahead and watch the video if it doesn't have sound. Hopefully it does. Okay, so that is linked to in our PowerPoint on Blackboard. So if there was no sound there, just go and watch that video directly. Now we're going to talk about acids, bases, and pH. And this is another one of those phrases that most people have heard of acids and bases. They've heard about pH, but they may not exactly know what acids and bases are. Well, first, both acids and bases are electrolytes. And electrolytes are just things that develop a charge when they are in water. Another way to say that is they are ionic when they are in water. Now, when we talk about electrolytes, we have to talk about dissociation. Dissociation means something falls apart when it is in water. And that's going to be our definition for acids and bases. Now, if you go on to take a chemistry class, you're going to have several definitions of acids and several definitions of bases, but for biology, for our class, there is going to be a really, really simple definition of an acid that we're going to use. And that is, what does it do when you put it in water? So let's look at an example. Let's look at something called hydrochloric acid, HCl. And we're going to look at what we mean by dissociation. When we put an acid in water, it's always going to do the same thing. It's going to dissociate. But we can go even further. It's always going to fall apart or dissociate in a very predictable way. It's going to fall apart and produce H plus and something with a negative charge. In the case of hydrochloric acid, the negative charge thing is going to be chloride. So HCl, hydrochloric acid, is an acid because of how it dissociates. When we put it in water, it falls apart and produces H plus and something with a negative charge. In this case, Cl minus. So that brings us to the other definition of an acid. Acids are proton donors. But that, I think, is too confusing for our class. So let's back up and see, why is it called that? Well, first, this thing right here, H plus. Let's look at exactly what that is. What is H? If we look back at our periodic table, H is hydrogen. And hydrogen was one proton, remember we'll just write that as H, and one electron. One proton and one electron. What happens if something was to come along and take that electron? Well, the electron is gone, and along with it, that shell that it is in is gone. So all that we're left with is the proton. But if we took away an electron, how do we symbolize H? If you lost an electron, remember, we write a plus sign. So this H is a proton. And since we've lost an electron, there's our positive charge. H plus is a proton. Protons, H plus, hydrogen ions. Those are all the exact same thing. I will use all three of these words interchangeably. And remember, they're always the exact same thing. So let's say the definition of an acid is something that dissociates or falls apart when we put it in water to produce a proton and something with a negative charge. Or it produces an H plus and something with a negative charge. Or we could say it produces a hydrogen ion and something with a negative charge, and that all means the same thing. So, like I said, sometimes you will hear a definition of acid is it is a proton donor. That means, well, donor, remember, means to give away. Acids give away protons when they are placed in water. Now we're going to come back and build on that definition when we look at acids and bases in just a moment. So here's our pH table. So what is pH? Well, pH is just a measurement of proton concentration. pH is a measurement of proton concentration. And here is from your book, the way that they show the pH chart. Here we see 0 going up to 14 and a couple of examples along the way. Now, typically when we think about acids, we think, oh, that's something like battery acid or stomach acid. And, yeah, that's true way down at the low end of the chart. But things like bananas, coffee, milk, those are acidic also. So acids don't necessarily mean that they are super corrosive and bad for you. Yes, the lower we get, the more corrosive they become. Now, if we go higher, then we are becoming less acidic. We say that we are becoming more basic. And as we get more and more basic, we get some of the same properties. At the far end, we have things like bleach and ammonia and oven cleaner. So bases or alkalines are also corrosive in strong enough concentration. It's not just acids that are corrosive, bases are also. So let's go ahead and go to our drawing area. And here I have our pH table. The pH chart runs from 0 to 14. Right in the middle is pH 7, and it is considered pH neutral. pH 7 is neutral. As you go below 7, the further away from 7 you get, the more acidic we are. So the lower the number, the greater the acidity. 0 is more acidic than 4. 4 is more acidic than 6. Now also, not only is it the lower the number, the greater the acidity, but the lower the number, the greater the H plus concentration. 5 has more H plus than 6. 4 has more H plus than 5, all the way down. And as we go further and further down, each step, the H plus concentration goes up, and we can be more specific. Each step, the H plus concentration goes up times 10. Another times 10. And another times 10. Every step of the way, H plus concentration goes up times 10. So let's, before we go and look at bases, alkalines, let's look at something. 3 has 10 times the H plus concentration as 4. But here's the trick. 2 has how much more H plus than 4? And here usually I ask students to raise their hand if they think that it's 10, or if they think that it's 20, or if they think that it's 40, or if they think that it's 100, or if they think that it's 1,000. And this is, I always see, one of the most confusing things for students to grasp at first. 3 has 10 times as much as 4. 2 has 10 times as much as 3. So 2 has how much greater concentration than 4? It is 100 times as much. Because remember, this is 10 times, not 10 more, 10 times more. So from 4 to 3 is times 10. from 3 to 2 is times 10. What is 10 times 10? 100. Now that's why 2 has 100 times the H plus concentration is 4. So that's acidity. Let's go and look at alkaline or base. Now base and alkaline, those two words are interchangeable. Base is the more common term, alkaline is the more proper term. I will try to use them both interchangeably. But here, when you hear the word alkaline, just think base. Now, as we go above 7, we are becoming more alkaline. And there's two ways to think about alkaline. Each step along the way, the H plus concentration goes down by 1/10. All along the way. Now, sometimes you will also see, as we go up, the OH minus concentration goes up by 10. The OH minus concentration goes up by 10. And we'll talk about why we see it written both ways here in just a moment. As we go up in pH, the H plus concentration goes down. So this down here at the bottom, 1/10 H plus each step of the way, is true. Sometimes we will also see OH minus going up by a factor of 10. So let's see why we can use those two things interchangeably. A common base is something called NaOH, or sodium hydroxide. Sodium hydroxide, NaOH. A definition that you will often see for bases also involves dissociation. When you put them in water, they dissociate or fall apart into OH minus and something with a positive charge. In this case, Na plus. Bases fall apart into OH minus and something with a positive charge, in this case, Na plus. So that's where the OH minus increase in concentration comes from. But all alkalines do not have OH minus. This is just common for them to. So what does that have to do with lowering the H plus? Well, let's say I put this in water and it falls apart into OH minus and Na plus. If there happen to be any free protons in that water, if there is an H plus floating around, what's going to happen when it comes into contact with this NaOH? Well, the NaOH is going to fall apart into Na plus and OH minus. Do you notice what's going to happen next? Well, the H plus is going to be attracted to the OH minus. Positives and negatives are attracted to each other. What do I get when I have H plus and OH minus? I end up with H2O, water. But what did I do along the way to produce that water? I pulled a proton out of that concentrated solution. I removed a proton. I removed an H plus. So that is why, as we go up in pH, the H plus concentration goes down, because the base is going to pull H plus out of that solution. Okay? Now, when I form this H2O, I have removed an H plus from solution, and that is how I got my definition of an alkaline. Now let's go back and look at something right here in the middle, pH neutral. Now pH neutral is 7 exactly. If it is 6.999, it is an acid because acid is anything below 7 exactly. If it is 7.0001, it is a base because alkaline or base is anything above 7 exactly. Neutral is 7 exactly. And something that is pH neutral, let's look at pure water. Pure water, H2O. Now, pure water, neutral, something that is neither acid nor base. But another way that we could think about it is pH neutral is something that is equally acid and base. What happens if I break a water molecule apart? If I break a water molecule apart, what I end up with is an H plus and an OH minus. What was the definition of an acid? Something that dissociates into H plus and something with a negative charge. Water did that, so water is an acid. What was the definition of an alkaline? Something that dissociates in water into OH minus and something with a positive charge. Water did that, but it did that equally as an acid and a base. So that is why water, pure water, is pH neutral. It is equally acidic and basic. Now let's go back to our PowerPoint. And look at normal pH for the body and pH homeostasis. Normal pH for the body is 7.35 to 7.45. So what does that tell us about the body? The body is slightly alkaline. It's tempting to think that the body is pH neutral, but it's not. It's slightly alkaline. It is above 7 exactly. And really, we can't deviate much from that. If we go much below that, it's called acidosis. If we go above that, it's called alkalosis. And if we go too far in either direction, we say that it is incompatible with life, which really just means it will kill you. Luckily, we have things in our body called buffers. And a buffer, by definition, is just anything that resists change in pH. We have several chemicals in our body. Something called the carbonic acid bicarbonate buffer system is going to be really important when we get to Bio 139. These chemicals, they will act like a base if our body starts to get too acidic, or they will act like an acid if our body starts to get too alkaline. They resist change in pH. Our kidneys, our lungs are buffers. The kidneys will start to remove H plus or OH minus. Not really OH minus, but something related to it if we go too far in either direction. Our lungs, well, one of the things that always blows students away when we get to that chapter in Bio 139 is the main reason that we breathe is to adjust our pH. Every time we breathe, we're breathing to adjust our body's pH. If we breathe faster or if we breathe slower, it's to bring our pH back to 7.35 to 7.45. Now, one of the things that I always talk about when I get to this point in the lecture is a pet peeve of mine. It is really common to see people talking about diets that will either acidify or alkalize your body. Well, those things are wastes of money because we have things in our body that prevent that from happening. We have these buffers that prevent that from happening. And if you can eat or drink something that does affect your body's pH, it means that your body has something wrong with it and you need to get to a doctor immediately. Anytime you see something that talks about changing your body's pH because of your diet is nonsense and don't waste your money on it. All right, so that wraps up the section on inorganic biochemistry. It was a pretty short lecture today compared to what we've been having, and we just have one more lecture over organic biochemistry, which we will have next. All right, if you have any questions at all, please text me, please email me. Otherwise, I will talk to you next time.